discussing organic chemical technology course, and in which we are discussing the module 6 regarding the petroleum refining, and we have discussed 5 lectures on different aspects of petroleum refining, starting from the introduction to petroleum refining industry. Then it was the evaluation of the crude oil, distillation of the crude oil, then some of the processes which are being used for improving the octane number and to use the residue which we are getting from the atmospheric and vacuum column. So, for in that case we discuss about the thermal and catalytic cracking. Now, we will be discussing in lecture 6 about the catalytic reforming process, which is one of the very important process that is being used in the refinery, not only in the refinery, but also in the petrochemical complexes where they are making the polyester or the purified terephthalic acid or DMT, because paraxylene, that is the basic raw material. So, here we will be more concerned about the catalytic reforming with respect to refinery, and while discussing the petrochemical we will be discussing about the catalytic reforming for aromatic production. Coverage of the lecture, that will be introduction, various catalytic reforming processes, because there has been continuous development in the catalytic reforming process from continuous, semi-continuous or the batch, and then the stages in the same thing has been happening in case of the catalyst also, stages in the historical development of the catalyst and also the engine scene, octane number of hydrocarbons, process step in the catalytic reforming, Naphtha hydrotreatment, because these are some of the Naphtha hydrotreatment, that is the integral part of the catalytic reforming for improving, for the reducing the sulfur content and the other impurities which are present in the naphtha. Classification of the processes, catalyst regeneration, which is part of the your catalytic reforming process, reactions in the catalytic reforming. Then we will be discussing in detail about what are the process variables in catalytic reforming. As I told you that the catalytic reforming is a major conversion process in the petroleum refinery and petrochemical industry. You cannot imagine a refinery without a catalytic reforming, because what happened in the initial stage of the refinery when there was no catalytic reforming many of the refineries, then at that time lot of the naphtha that was surplus. It happened in India also during the initial stage, even the Baroni refinery, which by Indian Oil Corporation, they were not having the catalytic reforming. Assam Oil Company, they were not having the catalytic reforming. So, lot of surplus naphtha was available at that time, and that naphtha was made available to the fertilizer plant. But with the coming of the petrochemical complex, naphtha cracker, and at the same time aromatic production requirement of the paraxylene, now we are performing the catalytic reforming for the production of the aromatics also. The reforming process is a catalytic process which converts low octane naphtha into higher octane reformate products for gasoline blending and aromatic rich reformate for aromatic production. Byproduct is LPG and hydrogen in the catalytic reforming process. Naphtha feed to catalytic reforming include low octane heavy state run naphtha, because the naphtha, light naphtha, which is having higher octane number, sometimes we call it the gasoline also, that is going to the gasoline pool, that is what we call it the state run gasoline. But medium and the heavy naphtha, that is going to the catalytic reforming process, or now we are going for the isomerization of the naphtha also. So, low octane heavy state naphtha is the feed for the catalytic reforming process. It transforms low octane number into high octane motor gasoline blending stock and aromatic rich in benzene, toluene and xylene with hydrogen and liquefied petroleum gas as a byproduct. Basically the process rearranges or restructures the hydrocarbon molecules in the naphtha feedstock as well as breaking some of the molecules into the smaller molecules, and at the same time during the process some coke formation is also there because of the hydrocracking and other reactions which are undesirable reaction. These are the some of the processes, catalytic reforming process which has been licensed, and the various development that has taken place, as I told you, the in the catalytic reforming reactor, and based on that these are the some of the technology that is available and the process licenses: rinforming, power forming, mag forming, ultra forming, Howdry forming, CCR plate forming, continuous catalytic reforming, octanizing. These are the some of the process that is available and the various type of the catalytic reformer we are using in this process. Status of the catalytic reforming units in India. As I told you, in the earlier stages many of the refineries were not having the even catalytic reforming or FCC. It was the only thermal cracking process or it was the fixed bed catalytic cracking. Similarly, in case of the catalytic reforming, that was not there, but now as I told you, we cannot imagine a refinery without catalytic reforming. So, there are about 17 reforming units in India, both semi regenerative and continuous reforming units are there, both gasoline reformers and aromatic reformers, because some of the refinery like BPCL, IOC Vadodara, Chennai, Cochin refinery, Haldia refinery, they are all producing the both they are the even in case of BRPL, Bogaigaon refinery and petrochemical, they are producing gasoline as well as aromatics also they are separating for the various end uses which is going as a chemical feedstock for production of large number of the chemicals. Just like benzene, we discuss about the LAB. So, benzene that is going for linear alkyl benzene, toluene for various other products that may be there, or toluene further it is converted to more value-added product, more useful product which has got more use like benzene and xylene. First xylene production in India was by the IPCL, now it is by Reliance, it is in the Reliance Industry, IPCL Vadodara unit. That is one of the largest integrated petrochemical complex. Octane number of the hydrocarbon. Why we need the catalytic reforming? Because you see the low octane naphtha which is not suitable for blending in the gasoline, we will have to improve the octane number, and octane number requirement of the fuel that is also changing, and so the octane number, as you know that we discussed while discussing the evaluation crude oil, the importance of the octane number in case of the gasoline and the cetane number in case of the diesel. So, octane number is a measurement of the anti-knock characteristic of the fuels. Among the same carbon compounds, the order of research octane number, paraffins and aromatics. Paraffin will have the lower octane number, then it is naphthenes, and the highest is in case of the aromatic. So, this is the order, and so that is why for the production of the high octane gasoline or aromatics, we do not prefer the more paraffinic feedstock, because again it will be more naphtha with less aromatic, and so that will be more suitable for the isomerization purposes. Just like in case of the some of the refining in Assam, we are having, and Numaligarh refining we are having the isomerization section also. Branch paraffin also have high octane number, it increases with the degree of branching. So, that is why we are state chain to more branch chain that is required in case of the paraffin, and this is what happening some of the reaction they are that is we are converting the linear to the branch chain. Therefore, oxygen number of naphtha can be improved by reforming the hydrocarbon molecules, that is the molecular rearrangement, the various constituents which are present in the naphtha. Such rearrangement takes place in reforming reactors in presence of catalysts by way of a numerous complex reaction, because a large amount of the reaction that is taking place during the catalytic reforming process. So, this I was telling about the octane number. Here you see the octane is 100, and then we compare with the octane. Normal butane, isobutane is higher than the normal butane, and pentane 61 and isopentane 93. Similarly, in case of the toluene, that is 119. So, the higher, if the your branch paraffins are there or the aromatics are there, then the octane number that will be high. Let us now discuss what are the various steps involved in the catalytic reforming process. First thing is the feed preparation, naphtha hydrotreatment, because what is happening in case of the naphtha, because lot of the impurities is present, especially the sulfur compound, nitrogen compound, and the some of the metals which are catalyst poisons. So, the some of the catalyst poisons that may be temporary and other may be permanent hardness, and that is the need of the requirement of the process, that the initial state of refinery itself we are removing the maximum metals which is present during the desalting process, and then whatever the sulfur compounds. But what is happening in case of the, because of the use of more and more heavier crude, the sulfur compounds they are coming in the naphtha and other product which you are getting from the crude oil evaluation, and so the pre-treatment of the feed before it is going to the catalytic reforming, that is very important. Another important step, that is the preheating, temperature control, because the major reaction which is taking place, the reaction in case of the catalytic reforming, that is endothermic. So, we will have to provide heat, and so for that the temperature in each stage we are having the inter-stage heaters. Catalytic reforming, then the final in the catalytic reforming reaction is taking place in the reactor, and then the catalyst circulation and regeneration in case of the continuous, because now we are having the continuous reforming process also. Stack reactors are there, the catalyst is moving, it is going for regeneration, and then here it is coming to the catalytic reforming reactor. Then comes the product separation, removal of the gases, because light component will be there, and that is always associated whenever you are having the high temperature, means the either you are going for the catalytic cracking or the catalytic reforming, some gases that will be always formed, and then so removal of the gases, that is very important. So, the product separation that includes removal of the gases and reform it by fractional distillation. So, the gases that will contain hydrogen, that will contain the your LPG, and hydrogen that is recycled in the process. So, for that you will have to have the proper separation. Separation of the aromatic, in case of the aromatic, that we will be discussing while discussing the aromatic production in case in the module 7 of the petrochemical part. Let us now discuss about the naphtha hydrotreatment. What are the various steps involved in case of the naphtha? Naphtha hydrotreatment is the important step in the catalytic reforming process for removal of the various catalyst poisons and to improve the performance of the reformer catalyst, because if the activity is going down, if the life is going down, if it is not stable because of the impurities, then definitely you will have to use more and more catalyst that will reduce the conversion, and so and that will upset whole economy of the process. So, the removal of these catalysts is poisons which may poison the catalyst is very important. So, what is happening in case of the naphtha hydrotreatment? When we are doing the naphtha hydrotreatment, it eliminates the impurities such as sulfur, nitrogen, halogens, oxygen, water, olefins, diolefins, arsenic, and other metals present in the naphtha feedstock to have longer life catalyst. Sulfur, as I discussed earlier, the sulfur that may be in the form of mercaptan, disulfide, thiophenes, which all these sulfur compounds will poison the platinum catalyst. The sulfur content may be as high as 500 ppm depending upon the type of the crude oil which you are processing. The heavier crude oil is there, so sulfur content that will be high. If you are having the low sulfur the crude oil, then they definitely the sulfur content. But in any case we will have to, because our requirement in case of the sulfur content in the final naphtha which is going to the catalytic reformer is 0.5 ppm or less, and water content less than 4. So, these are the various sections in case of the naphtha hydrotreatment: charge heater, reaction section, that is the main reactor, steeping section, and steeper boiler, reboiler. Fixed bed reactor containing a nickel molybdenum catalyst where both the hydrodesulfurization reaction and hydrodenatification reaction takes place. So, these are the actually the as in case of the also when you are using the naphtha, the natural gas which is going to the synthesis gas manufacturing, there also are removed. Same way here also the sulfur, that is by hydrodesulfurization is taking place, that is removal of the nitrogenous compound is also taking place. The catalyst is continuously regenerated, liquid product from the reactor is then steeped to remove the water and light hydrocarbon. This is about the desulfurization already discussed. These are the sulfur mercaptides, sulfides and disulfides react leading to the formation of the corresponding saturated or aromatic compounds. This is the reaction that is taking place. Denitrification, nitrogen compound in the naphtha are eliminated by producing ammonia. Oxygen compounds are eliminated by production of water. So, the process hydrodeoxygenation. Hydrogenation: olefinic compounds provoke coke deposit and are eliminated by formation of the saturated compound. Arsenic and metal compounds removal: arsenic, lead, mercury, sodium and other heavy metals which are present, they deteriorate the reforming catalyst and are removed by adsorption on the catalyst. Steeping section. Steeping section uses air for steeping the light ends, mainly hydrogen sulfide from the reactor product, and then the hydrogen sulfide is further going for the further removal from the gas stream, and then it is going to the Marox unit and other section. The steeper temperature, that is the temperature and pressure that we are maintaining. Steeper boiler, steeper reservoir supply heat required for steeper. Charge heater: preheating reactor feedstock to reaction temperature 340 degree centigrade. Charge heater has 4 passes, 4 gas burners. Heater tubes are made of stainless steel 321. Operating variables in the naphtha hydrotreatment: reactor temperature, space velocity, hydrogen partial pressure, hydrogen to hydrocarbon ratio, feed quality and steeper bottom temperature. This is the hydrotreatment of the naphtha. Feed is going to the heater, from the heater it is going to the main reactor where the hydrodesulfurization and other reaction that is taking place. We are having the catalyst bed, and after that the because the temperature here is high, it is going to the high temperature flash section and the low temperature flash, and then it is going to the steeper section. Here the gases which are separated, hydrogen that is going as such, because here the in the process we need the hydrogen, and after the steeper the desulfurized feed that is going to the catalytic reforming unit. So, this is the process which we are using in case of the naphtha hydrotreatment. Now, let us go to the catalytic reforming part. The classification of the catalytic reforming process: semi-regenerative catalytic reforming, cyclic catalytic reforming means you are doing the catalytic reforming, one reactor that will be bypass, continuous catalytic reforming, where the catalytic reforming is continuous, and at the same time regeneration of the catalyst is also continuous, and then it is being recycled. Semi-regenerative fixed bed reactor. In this type of the reformer, the catalyst generally has a life of 1 or more years between regeneration. The time between two regeneration is called a cycle of the reactor, and the catalyst retains its usefulness over multiple regeneration, but there is definitely some loss during the regeneration process. Cyclic fixed bed reactor. Cyclic reformers run under more severe operating condition for improved octane number and yields. Individual reactors are taken offline by a special valving and manifold system and regenerated, while the other reformer units are running continuously. And so, this is how the cyclic fixed bed reformers they are working. Continuous reformers. In these reformers, the catalyst is in the moving bed and regenerated not frequently, but continuously you can say. This allows operation at much lower pressure with resulting higher product of octane, C5 plus and hydrogen yield. These types of reformers are radial flow, because we are having the reactor axial or radial. So, here the reformer is the radial flow and are either separated as in regenerative unit or stacked one above one, because some of the refineries they are having the stacked reactor, reactor 1, reactor 2, reactor 3 and like that. So, they in each reactor your catalyst, the preheaters are there, regeneration of the catalyst is there. Semi-regenerative process is a low platinum and regeneration is required only once a year. The process consists of typically 3 reactor beds and furnace preheaters in each stage, because normally the 3-stage reactor, 3 reactors are running in series, and so they continuously from one reactor to another to third reactor, that is going the product from one reactor that is going to second to third, and in between we are having the interheater. The dehydrogenation is highly endothermic, because this is the main reaction which is taking place in case of the catalytic reforming, which is highly endothermic and large temperature drop as the reaction proceeds. So, that is the reason why we need the preheating of the naphtha feed, which is coming from one stage to another stage after reforming. I am saying the naphtha means the reformate of number 1 diester, that will go for preheating, second again it will go for preheating, just to maintain the temperature around 500 degrees centigrade, which is the requirement, because too low or the too high temperature, that is also going to affect the operation of the catalytic reforming process. That we will be discussing while discussing the process variables. Dehydrogenation of the naphthenes takes place in the first reactor. That is how because we are having the some reaction is taking place in the first reactor, second reactor and third, like that. So, dehydrogenation of the naphthenes takes place in the first reactor and require less catalyst. Preheat of the feed is required. Last reactor for isomerization of the paraffins, typical catalyst distribution is 3 reactors is 20, 30 and 50. Catalyst regeneration. Why we need the catalyst regeneration? Because that is in all cases when we are having the either the catalytic cracking or the catalytic reforming, because the temperature is around 500 degrees, some coke formation is there, that you can minimize, but you cannot avoid completely. So, what has happened? Now, the catalysts in all the cracking process or the catalytic reforming which has been developed, now they are having the more resistance towards the coke. So, the coke formation and the coke formation also that can be reduced. So, coke formation contamination on active site, agglomeration, catalyst poisoning. Catalyst could be restored if the deactivation occurred because of the coke formation or the temporary poisoning. So, this is the problem in case of the why we need the catalyst regeneration, because again the regeneration or the catalyst life, that will be totally dependent upon the type of the feedstock, the efficiency of the pre-treatment processes which you are doing is naphtha hydrotreatment process, because the impurity removal to the required limit which is required for the catalytic reforming, that is very important. Objective of the regeneration, surface area should be high because that is the basic requirement in case of the catalytic reforming or any catalyst, because the coke, fine cokes that may deposit on the surface, and so that is reducing the surface area as well as they will poison the catalyst also. Metal, platinum should be highly dispersed, acidity must be at a proper level, regeneration changes by the severity of the operating condition. Coke formation can be offset for a time by increasing the reaction temperature. This is I was telling about the catalytic reforming process. Here the naphtha after the pre-treatment, that is the pre-treatment section, naphtha pre-treatment section which is having the preheating, then the pre-treatment of the naphtha, and then the other units are also there. So, that we have already discussed. Then the chloride addition is also there, importance of the chloride is also there, excess chloride is also not desirable. So, after the naphtha pre-treatment, that is going to the heater, and from the heater it is going to reactor 1. From the reactor 1 the product again it is being preheated in the heater, and then it is going to the second. After the preheating, again in the from the reformer the product that will go to the reformer number 2 after the preheating, and like that the all the in the 3 stages we are having the, here preheat furnace I have shown only one, but this is all the 3 furnaces we are having. And after the reformer 3, the final product which you are getting, that will go to the, because the heat of this all the reactor that we are utilizing here for preheating, and so the after the cooler it will go to the light end column. Again as I told you during the process we are getting hydrogen and LPG also, that will be actually again that will depend upon the your operating condition, whether the light ends are more or less, it will depend upon the temperature. Then the flash dump and flash dump to the formally the you are it is going for the reformat stabilizer, where the C3 C4 component lighter component that will be separated, and the reformat the finally which you are getting, that will be used for RFG reformatted gasoline, or it may go for the separation of the aromatics in the aromatic plant. So, the choice of the feedstock also will be decided whether we are going for the reformat or the gasoline pool, or it will go for the aromatic production. So, I think the whole diagram, the flow diagram of a catalytic reforming. What is happening in case of the stack reactor, I have not shown here, but stack reactor, one bottom reactor, number 1 is at top, number 2, number 3 reactors. So, stack reactors are there in case of the catalytic reforming, continuous catalytic reforming process. So, reactions, what are the reactions that is taking place in case of the catalytic reforming? These desirable reactions, because in case of the catalytic reforming any reaction always there is some side reactions which are not desired, but that is taking place. So, here also in case of the catalytic reforming we are having the 2 types of the reaction which is taking place, one is the desirable part and the non-desirable part. So, desirable reaction, dehydrogenation of naphthene to aromatic, this is one of the very important reaction in case of the catalytic reforming process, and this is endothermic, and that is the reason why we need the preheater in each stage in case of the catalytic reforming process. Then the isomerization of the paraffins and naphthens. These are the again very important, because we need more branch paraffins so that the octane number is increased. Dehydrocyclization of the paraffins to aromatics. Some of the non-desirable reaction which will be there, only you can reduce the extent of these non-desirable reaction, that is the hydrocracking of the paraffin to lower molecular weight compounds. Then the formation of coke, that will also result. And so, let us discuss in detail about the dehydrogenation reaction. Dehydrogenation reaction are very fast, about 1 order of the magnitude faster than the other reaction, highly and this is the reason you see the catalyst distribution in the first reactor, that is less, second higher than the one, and the third is the or much higher catalyst that we are using. So, the reaction is highly endothermic, cause decrease in the temperature, highest reaction rates, aromatic form have high boiling point. So, end point of the gasoline rises. High boiling point, that may be required because the less your vapor pressure, that will affect the vapor pressure of the gasoline. Naphthenes dehydrogenation, the reaction is highly endothermic and favored by high temperature, low pressure. So, you will have to have the optimum condition. Kinetically, the rate of reaction increases with the temperature, not affected by the hydrogen partial pressure. Rate of reaction is high, the reaction is promoted by the metallic function of the catalyst. Because now they will be discussing about detail about the catalyst. The catalysts are the bimetallic metal function and the acid function catalyst. This is the reaction that is taking place here, actually cyclohexane that is converted to the benzene. Dehydrogenation favorable condition, already we discussed high temperature, low pressure, low space velocity, hydrogen to hydrocarbon ratio, as I told you, that is not having significant effect, and this is another reaction that is taking place during the dehydrogenation. Paraffins dehydrocyclization, this is also one of the that is the multiple step process involved a dehydrogenation of the normal paraffins or the isoparaffins. This is the dehydrocyclization, with a release of one hydrogen mole followed by a molecular rearrangement to form a naphthene and the subsequent dehydrogenation of the naphthenes. Dehydrocyclization is promoted by both catalytic and the metallic and acidic function, and is favored at low pressure and high temperature. Isomerization, linear paraffins isomerization, these reactions are fast and slightly exothermic. Thermodynamic equilibrium depends mainly on temperature, pressure has no effect. High temperature favors isomerization. In case of the isomerization, branch isomers increase octane rating, that is why we are having the isomerization and we are producing more branch paraffins. A small heat effect, fairly rapid reactions is there. Already we discussed about the dehydrocyclization, naphthenes dehydroisomerization. A ring rearrangement reaction formed alkyl cyclohexane dehydrogenates to aromatics, octane increase is significant, reaction is slightly exothermic. Favorable conditions, high temperature, high pressure. Here you see the high pressure, somewhere you know the low pressure. So, that is the optimum condition that has to be maintained in case of the catalytic reforming process. These were some of the desirable reaction which is taking place in improving the octane number of the. Now, let us discuss what are the undesired reaction. First undesired reaction that is taking place, that is the coking, the formation of the coke because of the cracking process that is taking place in the process. So, coking is very complex group of chemical reaction linked to heavy unsaturated process such as the polynuclear aromatics, because that the contains polymerization from precursor to the coke formation that is taking place. So, traces of heavy olefins and diolefins promote coking. High feed boiling point favors coking. Poor feed distribution in the reactor promotes coking favored by high temperature. Hydrocracking, exothermic reaction, slow reaction, consume hydrogen, produce light gases, because normally in case of the hydrocracking the lighter gas. So, we will be losing the reformate. So, that is the our interest is not in the lighter products, our interest is in the more reformate which will be used as a gasoline or for the aromatic plant. Produce light gases lead to the coking, cause high paraffin concentration. This is the cause, because the more paraffins the chances of the coke formation that will be more. Hydrocracking, as I told you, this is the exothermic reaction. The main effects of the hydrocracking: loss of the reformate yield, decrease in the hydrogen production and increase of the LPG production. The reaction is promoted by both metallic and acid function of the catalyst. Now, let us discuss about the what are the process variables in case of the catalytic reforming, because this is very important part in case of the catalytic reforming or any reaction. The operating condition that has to be maintained properly to have the optimum yield. So, here the some of the major parameters which is affecting the reformate yield or the quality of the reformate, octane number of the reformate. First is the feed characteristic, reaction temperature, space velocity, reaction pressure, hydrogen to hydrocarbon ratio. These are the actually I was telling about the favorable condition of the operating parameters which are there: dehydrogenation of the naphthenes to aromatics, low pressure, high temperature that is required. High temperature means not more than, if you are going beyond 500 to 510, the other side reaction that will be more predominant and the formation of the coke is there. Isomerisation of the naphthene, interterminate, indeterminate, dehydrocyclation of the paraffins, low pressure, high temperature, hydrocracking, high pressure and the high temperature. Reaction temperature. Reaction temperature is the most important operating parameter. What is happening? By simply raising or lowering the reactor inlet temperature, operators can raise or lower the octane number of the product. But at the same time, if you are going for the higher temperature, then the loss of the reformate will be there. Since all the reactors inlet temperature are not necessarily identical, it is commonly accepted to consider the weighted average inlet temperature. Feed quality. Feed quality, that is very important, and depending upon whether we are operating the reformer on the gasoline mode or we are operating on the aromatic mode, because again in case of the aromatic production, whether we are interested in in benzene, whether we are interested in paraxylene, accordingly you will have to take the feed quality or the naphtha which are there. If the you are going for the aromatic of the whole range, then you will have to take the 90 plus to because you see the boiling point of the benzene is around 90, toluene is around 110 and the xylenes that is 136 to 140 degrees centigrade. So, depending upon the requirement, you will have to adjust the feed quality and the type of the naphtha which you are taking. So, naphthenes dehydrogenate very fast and give rise to. So, therefore, N plus 2A is taken as index of reforming. Higher the N plus 2A, naphthenes and aromatic. Higher the N plus 2A, better is the quality to produce high aromatics. So, N is the naphthene, A is the aromatic. That has been correlated with the characterization factor also, because the characterization factor is also giving idea of the whether the feed is the naphthenic or the paraffinic or intermediate. So, about the feed quality, I was telling the lighter fraction have a poor naphtha and aromatic content are high, therefore, poor feed for the reforming. Low IBP feed results in lower aromatics and hydrogen yield. Heavy fraction have high naphtha and aromatic hydrocarbon content, therefore, good reforming feed, but tendency of the coke formation is high. So, that is why heavy fraction is also not accepted. So, temperature, I was telling about the temperature, already we have discussed about the temperature part. Space velocity, because these are the two terms normally we are using in the case of the space velocity. One is the liquid hourly velocity, another is the weight hourly velocity, and this is the actually how the LHSP, liquid hourly velocity, and weight hourly velocity, volume upon hour of the reactor charge, and divided with volume of the catalyst, and weight hour of the reactor charge divided by the volume weight of the catalyst. Reforming LHP should be in the range of 1.2 to 3.0. So, below 1.0 LHP, undesired side reaction, namely hydrocracking, occurs, which reduces the reformate yield. For every rise in the LHP, 0.1 between 1 to 2, about the 2 degree centigrade rise in the temperature is required. The lower the space velocity, the higher the severity, assuming all other condition changes. I told you the rise in the temperature, that 2 degree rise in the temperature. So, lowering the space velocity has the same effects as increasing the temperature. Increase the oxygen, decrease the product yield, decrease the hydrogen purity, increase the coke deposit. Reaction pressure, this is the pressure normally you are maintaining. Decreasing the pressure increases the dehydrogenation of the naphthene and dehydrocyclization of the paraffins, which favors an increase in the production of the aromatic and hydrogen, increase catalyst coking and shorter cycle life. Higher pressure causes higher rates of hydrocracking, reduces the reformate yield, but decreases the coking of the catalyst, resulting in the longer life. So, again you will have to take a optimum condition in case of the because some reactions are favored, some reactions are not favored by the pressure. Hydrogen to hydrocarbon ratio, that is very important actually in case of the catalytic reforming process, and this is defined by the hydrogen hydrocarbon ratio, moles of hydrogen in the recycle divided by the moles of the hydrocarbon. Main purpose of the hydrogen recycle is to increase the hydrogen partial pressure in the reaction. Hydrogen reacts with the coke precursor, removing them from the catalyst reforming polycyclic aromatics. Higher the hydrogen to hydrocarbon ratio, higher the cyclic length. Two main reactions for reducing hydrogen and hydrocarbon ratio. This is also another effect of hydrogen to hydrocarbon ratio, reduction the energy cost for compressing and recirculating hydrogen, favors naphtha dehydrogenation and dehydrocyclization reaction, lowering hydrogen and hydrocarbon ratio from 8 to 4 carbon, increase in the 1.75 times, and from 4 to 2 carbon increases 3.6 times. This is the process variables which we discussed. Just to summarize, the effect of pressure increasing or decreasing on the what is the effect of the pressure, temperature, space velocity, hydrogen to hydrocarbon ratio, feed A plus 0.5 N, final boiling point and initial boiling point of the feed, and depending upon that the research octane number. If the pressure, increasing the pressure, that will decrease, increasing the temperature, that will increase, space velocity, that will decrease the octane number if you are increasing. So, this is the how the effect of the various parameters which we discussed are there. Similarly, in case of the reformate yield also, you can see if you are increasing the temperature, means beyond the optimum temperature, then the you will be losing useful material, means the reformate, there will be reduction the reformate yield. Hydrogen yield, that will be also affected by the various operating parameter, co-formation, that as I told you, that is the, if you are decreasing, then the more coke formation, temperature increase, again the more coke formation, and these are the some other parameters which affect the coke deposit. Now let us discuss, because as I told you, there has been continuous development in the catalytic reforming, because there has been changes in the quality of the naphtha, and at the same time a requirement of the octane number, gasoline, requirement of the even the aromatics, whether you anticipate for paraxylene, whether you anticipate more aromatics, like that. And so depending upon that, there has been continuous development in the catalytic reforming catalysts, and indigenous catalysts also that has been developed. So the catalysts are monometallic, bimetallic, acid activity, that is the halogen, silica incorporated in alumina, they give the acid, because both the acid and metal function of the catalyst, they are having the different role. Stages in the historical development, the reforming catalyst in Indian scene, development of the low platinum monometallic catalyst, that was first IPCL, now it is Reliance for the benzene toluene production, commercialization of IRC 101 catalyst in the first reactor of the IPCL, 3 reactor system of the xylene production. Scale up and manufacture of IPR 2001 at IPCL Catalyst Division, commercialization of the bimetallic catalyst at MRPO for gasoline production, commercialization of the bimetallic catalyst, solid. Now let us discuss the two functions which I was telling in case of the catalytic reforming catalyst, metallic function and the acid function, and each function they have different role in the catalytic reforming reaction. So metallic function, it promotes the dehydrogenation and the hydrogenation reaction, it also contribute to the hydrocyclization and isomerization. Acid function, it promotes isomerization, the initial step in the hydrocracking, participate in the paraffin dehydrocyclation. Advantage, what are the advantage, why we have gone for the bimetallic or the multimetallic catalyst? Enhance the resistance to coke. As I told you, now the catalysts are being developed, they should have more and more resistance towards coke, more resistance towards this sulfur compound, lower foiling, higher coke tolerance, longer cycle length for your reforming units, low pressure and low hydrocarbon ratio, because that is also, if you are increasing hydrogen, then the other your operating cost, that is increasing. So these are the some of the advantages. Just to summarize, high octane, high aromatic, high yields of the desirable products, better yield stability, lower temperature requirement, better tolerance to high temperature, better regenerability and high ultimate life. Now let us discuss about the two slides on the catalyst poison, because the catalyst poisoning that affect the whole working of the any reaction system. So we are having, in case of the naphtha, we are having the two types of the poisons, catalyst poison. Not only in case of the catalytic reform by any reaction, we are having the two types of the poisons. One is the temporary poisons, or those impurities which can be removed during the various pre-treatment process, like sulfur, nitrogen and some of the metal. Now the new of the catalyst which we are having, metal removal is also taking place. Permanent poisons are those impurities present in the feed which is irreversible damage to the catalyst. So that is the reason why the maximum removal of the metals, that has to be there. these are the actually the various maximum level of the catalyst poison: arsenic, lead, copper, mercury, and so this is the from where various sources from where these are coming, that may from the cracked naphtha, recycle, corrosion, naphtha condensate, corrosion, then the foaming additives, corrosion, and so this will be the actually, but this is the maximum level that is required in case of the. So this was about the catalytic reforming process which is being used in case of the refinery, and that is one of the very important process. Another development that has taken place in case of the refinery, that is the just to improve the quality of the naphtha, to have the higher gasoline, that was the actually isomerization, alkylation, and the aromatization process. So, in the next lecture we will be discussing about the more alkylation process, isomerization process, and the polymerization, which also actually it is the oligomerization, not the actual polymerization. So, there should not be any confusion.